please.
Thank you very much. And first of all, thanks to Roland and to the organizers for inviting me. This was very nice. So I'm going to talk today about something that is a bit different from what we have seen, because I will be talking about excited states, electronic excitation, and I don't know if this works. I'm going to come. So, okay, thank you very much. And this electronic excitation will occur in complex environments. So why do we need to talk about complex environments? Because a lot of chemistry actually occurs in some kind of condensed phase, which could be a solution, could be a protein complex, could be any kind of material. And when you are in condensed phase, you have a molecule, let's say, surrounded by an environment. You can have a lot of different interactions between the molecule and the environment. In particular, you have an interaction with the bulk, and you also can have specific interaction that depends on the nature of the atoms in the molecule and in your environment. In particular, when we are talking about excited states and excited state processes, these are really affected by the surroundings, by the environment of the system. So, for example, processes like absorption and fluorescence, excited state dynamics, and all spectroscopies depend on the environment where we put the molecule. So there are several ways to describe the environment of a molecule in quantum chemistry. Two of them are continuum models, where we don't describe the environment in its atomistic detail, but we use a dielectric. Maybe most of you know about these continuum models. And then we have, which are called those implicit salvation. And then we have atomistic models. So for example, in QMMM, which has already been introduced, we have the atoms of the environment that are described at some kind of molecular mechanics level. And then what we have is polarizable QMMM, which is called also QMMM pol, where we also allow the MM part to polarize in response to our QM molecule. And it's really important to use this kind of methods when we describe excited state processes, because we need to describe the mutual polarization, the mutual effect between the molecule and its surroundings. So there is a kind of motivation. The other part of the motivation is that we have heard about a lot of machine learning models for ground states. We still haven't heard much about excited states, but there are machine learning models for excited states. For example, for absorption spectra, also for two-dimensional spectroscopy, okay, and for non-adiabatic dynamics. But what if we need to describe a more complex environment where these excited states occur? So what could be a complex system? What could be a complex environment? So one really complex example is these light harvesting complexes, which are pigment protein complexes, where you have an aggregate of like different pigments, and there is a lot of diversity in here, where you have this aggregate of system. These are called multichromophoric, because we have a lot of chromophores packed together in a protein complex. And of course, I didn't show the protein here, but around each of these molecules, you have a lot of protein residues. So all of these are in some kind of unique protein pocket. And when you want to know what is the response of this thing to light, which are the optical properties, well, this depends on both the interaction between the pigments, these are called excitons, exciton interactions, and the interaction between the pigment and their environment. So this is something a bit complicated to describe. So there are several factors that affect the optical properties of the system. So if we want to be able to describe the spectroscopy of such a complicated system, we need to know what we have to look for. So one thing I already talked about is the interactions between excited states of different chromophores, which are called couplings. And then we have the interaction with the environment, which we call solvatochromism, but since we are not in a solvent, I will call it electrochromism. And then, since we have a protein pocket, the protein pocket will distort in some way each pigment, so we have also a geometric effect. And all of this doesn't stay fixed, so proteins are very flexible in general, so we will have a lot of disorder in the system. So we need to describe all of these effects. And what is the state of the art of describing this? Well, we need a model that is able to describe the environment of the pigments, which is highly heterogeneous because every pigment stays in a different pocket and is composed by the protein, but also maybe a biological membrane and the waters, and is also flexible. So, and since we have a lot of pigments within the same proteins, and we could have a lot of chemically totally identical pigments which stay in different protein pockets, so they will have different properties. So they have different properties because they are in different environments. And this is the thing we need to describe. So what we use is this polarizable QMMM. So you probably all know about QMMM. You have a QM part, and you use some charges in the MM part to describe that create a potential, a field that acts on the QM part. But this is not enough for excited states. So we need also to describe the fact that the MM part can polarize in response to an electronic excitation. So what we use is polarizable MM, which is described with fixed charges on each atom and induced dipoles. So an electronic excitation will be able to induce some response also in the environment. And this looks already quite complicated. But since we have multiple chromophores, we cannot just treat one chromophore at the QM level and everything else at the MM level. We need to be able to describe the collective excitation of the entire system. So let's talk about one of these systems could have 10 to 20 chromophores or more. So we need another kind of multiscale strategy, which is this exciton strategy, where we want to describe the excited states of an aggregate of chromophores as a superposition of states of excited states on each chromophore. So it's something like this. You construct your excited state as a sum of excitations localized on each chromophore. And if you do that, you can describe this excitation with a model Hamiltonian that looks like this. And basically, you only have to compute the site energies, which are the excitation energies of the localized states. So one chromophore is excited. And then these couplings, which are basically just the interaction between the transitions on different chromophores. So in this way, you would be able to reconstruct the excited state of a very large aggregate just from calculation on single chromophores. So this is already very nice. On the other hand, since these systems are very disordered, this disorder, the fluctuation of the protein, will affect both the excitation energies of the pigments and the interactions, the couplings between the pigments. So you would want to use molecular dynamics to sample the conformations of this complex. And you will get an ensemble of structures that in turn gets you an ensemble of different excitation energies, an ensemble of different Hamiltonians. So this is also useful because usually we have crystal structures for these complexes, but they are not accurate enough. So basically, if you want to describe this kind of system, you need to do quite heavy calculations. Even if you only do DFT calculations, the pigments are large, you have a lot of pigments, and you have a lot of samples from molecular dynamics. So what's currently done is you take your system that you can see how many, these are all pigments, how many pigments are there, and you take a molecular dynamics, you take samples from this molecular dynamics, and on each sample and on each pigment, on each chromophore, you perform an excited state calculation. So you easily go to hundreds and hundreds of calculations, maybe thousands, with hundreds of samples for times maybe 10 or 20 pigments. So you already have thousands of calculations. So what we thought here is, why don't we exploit the fact that we need to do all of these calculations to train some machine learning model. Since we already have to do all of these calculations, why don't we exploit them, and next time we only run the prediction. So we turned to machine learning, and we wanted to use Gaussian process regression because it kind of works better with not so many samples. So Gaussian process was already introduced very nicely yesterday, so I won't talk about that in detail. I want to show you how to use this to learn excitation energies in a complex environment, in a protein environment. Now this works for a protein environment, but there is nothing really different about this environment with respect to something else. For example, a solvent. So the idea is that if you have an environment and you want to compute the excitation energy, the excitation energy will be the excitation energy in vacuum, in gas phase, plus some modifications, some shift due to the environment. And we have a shift due to the charges in the environment, and another shift due to the induced dipoles in the environment. And we can compute all of this because we can compute excitation energy with a QM method, with a QMMM method, or with a polarizable QMMM method. So if you do a QM calculation, you get the excitation energy, of course, in gas phase, and anything that changes, all the changes is the internal structure of the molecule. But if you do a calculation with QMMM, you get the response to the charges. So you get the first two terms of this sum. And if you do a calculation with polarizable MM, you get all three. So in this case, the excitation energy depends only on the internal structure, and in this case, it depends on the charges that are present in the environment. So how do we learn this? Well, we want to split the task into different parts. One would be learning the excitation energy in vacuum, and this is already well known. We actually use Gaussian process on the Coulomb matrix. So it looks something like that. You have a kernel that depends on two Coulomb matrices, and you get the coefficients that reproduce the excitation energies in vacuum. This is really simple. But then we want to reproduce the shift, which is this delta that depends on the charges. So now the shift would be calculated as excitation energy at the QMMM level minus the excitation energy in vacuum. So this is the shift due to the charges. And of course, this shift depends on what charges you put in the environment. And how do you describe that? Well, we use as a descriptor the electrostatic potential at the atom, at the QM atoms. Okay, so here it's a very simple descriptor that only scales as the number of QM atoms. So it's really simple. But then, if you have two different geometries of your molecule that are in the same environment, they could have a different response. So we add another kernel that describes how this response to the potential is changed by when you change the geometry of your molecule. So here you multiply a kernel that depends on the electrostatic potential and another kernel that depends on the internal coordinates. And then you do your kernel regression task. And you reproduce this. Then you can do the sum and obtain the excitation energy in the environment. Now we are only left with the polarization contribution, which is a bit more complicated, but it turns out that physically, the contribution of a polarizable environment to the excitation energy is simply something like that. You have a transition in your QM part. This transition induces a response in the environment which interacts back with the transition. So it turns out you need, with this polarization part, only depends on the transition density of the QM part. So the transition density is a generalization of the transition dipole. So we can represent again the transition density instead of an actual density as charges on each atom of the molecule. And this simplifies the expression. And then we only need to know the transition, these transition charges, to compute the polarization contribution to the excitation energy. So it turns out that learning the transition charges is very easy because you only need a linear model. And then you need another linear model to take into account that you have charges in the environment which amplify, which change the transition density. And so in this way, you would be able to compute, to learn excitation energy in an environment. So let's see the results. So our training set would be this complex that contains a lot of different chlorophyll pigments. They are divided in chlorophyls of type A and type B. They are different molecules, but we have a lot of different chlorophyll of different pockets in which we have the same chlorophyll A. So we see that with quite small dataset size, we get nice errors with respect to the target. But then, if we look at the averages, so we average over the molecular dynamics, and this is only on test frames, we see that we get the same ordering of excitation energies, more or less, as the actual QMMM calculations. So we are able to reproduce the fact that each different chlorophyll in a different protein pocket has a different excitation energy. So this is very nice. But then we also evaluate the performance of the method on a completely different complex, which has the same chlorophylls A and B. And for single MD frames, we get a very nice agreement with the target. So these are not the excitation energies, these are just the shifts due to the environment to better see that it works. And finally, we wanted to see if our model could extrapolate to completely different environments. So we used the training set as before, but then we tried to reproduce the excitation energy of this chlorophyll in a solvent. So we computed with DFT the excitation energy in methanol solvent, and this the shift due to QMMM, and we get again a quite nice agreement with the target. And so this model was not trained on methanol; it was trained on the protein. So if you change completely the environment, it still works. So now we can use this method also to explain the effect of each amino acid of the protein on the excitation energy. So what we do is simply turn off the charges of a specific amino acid and record the effect. And now we also tested it, so this is the yellow points are the prediction of machine learning, of the machine learning model, and the blue points are the real shifts when we turn off residue, and it works quite well. So we can use the machine learning model not just to predict the excitation energies in a light harvesting complex, but also to see if I change a residue, if I remove a residue, how does this excitation energy change? And this would be useful because we explain each different pockets, each different protein pocket, how does it influence the excitation energy of the pigment. So now I will go fast. We also have a linear model for the couplings because since we can compute the transition charges, we can compute also the excitonic couplings. And actually, we put everything into a code that does the prediction of the entire exciton Hamiltonian of the system. And then we can also apply this method. So to test this method on a quite difficult task, we used two different complexes, a wild-type complex and a single mutant. So we performed the molecular dynamics on these two complexes, and we computed all of our Hamiltonians with machine learning. So we computed 6,000 exciton Hamiltonians with machine learning, and we used these Hamiltonians to compute the absorption spectrum of the wild type and of the mutant. And they are very similar, of course, not the same. So if you look at the difference, we have some difference. So this would be the different spectrum. But if you look at the experiment, it looks really similar. So this is a very, very tiny effect of the mutation, and we are able, with only the machine learning, which was trained on a different complex, to still reproduce this very small difference. Okay, we don't stop here. 2 minutes. We wanted to try a more challenging case, which are these cardinal pigments. These are polyenes. They're very difficult to describe from quantum chemistry. But from the machine learning perspective, we wanted to see if we were able to describe the effect of the environment on the excitation of this molecule. So it turns out that in this case, the shift due to the environment is not linear in the potential. This is because this molecule is basically symmetrical. So the first effect would be second order. We actually already heard about this yesterday. So this would be some kind of effect of polarization. So we changed our kernel, and for the environment we use a polynomial kernel to be able to capture the nonlinearity of the shift with the potential. And then we trained again the model on the complex and cross-predict in other environments. And okay, this is not the training set. These are samples taken from the test set, and it works well within the complex, but it still works quite well in the environment. And this would be a normal methanol environment, and this would be a methanol environment with randomly added charges. So here the effects are much, much, much larger, but still we are able to predict them. Okay, so I will go through the conclusions very fast. We use a physically sensible kernel to capture the electrostatic response in QMMM calculation. And this model works really well and can also extrapolate outside the proton environment. And we also learned the transition charges, so we know how to compute the polarization effect and decouplings between the pigments. And this model can reproduce very, very, very small effects of mutations. So we want to go further and try to compute a complete machine learning database for this kind of systems, and probably use delta ML to target more accurate methods. And then we also have some other possibilities. And what I just want to say is that this framework works with this system. There is no reason why it shouldn't work with other protein-bound chromophores. And would like to thank the group, the molecular group in Pisa, and especially Edoardo, who did most of this work, and Patrizia Mazzera and Amanda Arcidiacono, who did part of the coding. And thank you very much for your attention.
Thank you very much. We have 1 or 2 questions before the coffee break. So up there.
Hey, Lorenzo, very nice work. Just on that last point, exploring other complexes, how far can you push this if you're thinking about, for example, the reaction centers, which are downstream from the light harvesting complexes?
So thank you for the question. For the reaction center, basically the only thing that is missing here is the description of charge transfer states between one pigment and another. So we are also working in this direction, but of course it's a bit more complicated. But I think it's doable.
Any further question? Please.
Thank you for the nice talk. I have just a quick question. I was curious for your methodology. So when you're looking at different mutants or changing the pigment, like I don't run this kind of calculation, so I'm curious how quickly you can compute the spectra. Like what's the time scale for these calculations in terms of GPU hours or something? How much time does it take to actually get the spectra, given that you say make a mutation to your LHC or change the pigment?
Here, probably the most difficult thing would be running the molecular dynamics. That would be the slowest part. So in these systems, we probably get a few microseconds in a few weeks.
Oh, okay. It's
and
quite long.
Then running all this 6,000 calculation prediction takes about less than 1 day. Now I don't know exactly. And the most difficult part is computing the polarization response, because this requires actually computing the response of polarization. But we actually have linear scaling models for polarization, which we are not using right now in this case.
Okay, thank you. Very interesting.
Okay, we thank the speaker once more.